this talk is on what degree the ETAS model, which is now used as the standard model for testing hypotheses associated with earthquake clusters, can produce Foreshock phenomena and the Båth law. The Foreshock in the ETAS model we can simply define as a background event that triggers a larger event directly or indirectly. The Båth law says the largest aftershock is about 1.2 smaller than the main shock. In 1995, Båth found this formula should be, the difference should be right as a function of a linear function of the main shock magnitude. So the question are, how much can the ETAS model explain the Foreshock and the Båth law? And the consequence of a general earthquake cluster model like the ETAS model? On the Båth law, they have already many studies to see whether it is an independent physical law or not. The ETAS model is defined through the time dependent and observation history dependent seismicity rate function. In particular, those two exponential laws, one is one for the productivity function, one for the probability form of the Gutenberg-Richter law, magnitude frequency relation, as a key points in the following theory analysis. The critical parameter given by the average number of this direct upsprung triggered by an arbitrary earthquake determines the whole process, whether it is stationary or it grows into a population exploding after a certain time. The main equation which gives the probability of the largest upsprung triggered by an earthquake of magnitude m is less than m prime. So this equation was obtained by several researchers. The probability that an event is a Foreshock can be obtained by setting m prime equals to m. Here is the solution of the main equation. By introducing this function f, the probability that the biggest event in an earthquake cluster is greater than m. This equation becomes much simpler. Here are the solution of f of m. When the process is supercritical because the number of population in the cluster might be infinite, so there are always some probability the earthquake including infinite numbers of any magnitude. Here are the given f of m. Here we can calculate the function zeta. The diagonal line shows the probability that the events of corresponding magnitude are not Foreshocks. If we plot the complementary function for the of the diagonal, we have the Foreshock probability for different magnitude. For the critical ETAS model, this probability tends to a constant. For subcritical case, this probability drops to 0 when the magnitude grows. Applying the above theory to the JMA catalog, we plot, we obtain those two plots. The left one is calculated based on the ETAS parameters from data fitting. The right panel is calculated through smoothing earthquake clusters by using the stochastic clustering method. We can see the Foreshock probability is below 1% for very big magnitude and up to something like more than 10% for magnitude 4.2. Let's come to the Z function again. This figure shows the subcritical case. For large magnitude, Z can be approximately a function of a linear combination of those two magnitudes, m and m prime. For the critical case, when alpha is bigger than half of beta, zeta is a function just of the magnitude difference. When alpha is less than half of beta, the function is the difference of alpha and half beta. Here is a summary of the Båth law and the ETAS model. The original Båth law only holds for the critical case when alpha is big enough. Otherwise, the Wootz formula is correct. All of those forms are in the function of a double exponential distribution. Here is a simulation of the Båth law using the ETAS model done by Arnes and Helmstedt and Didier Cernich. And come back to the JMA catalog again. This is the white line as a median of can be reprint the formula, Wootz formula, as a linear combination of the two magnitude. And for the volcanic region, alpha is usually very small. Here, I use the data from the central volcanic region in New Zealand. After stochastic clustering, against the magnitude of the starting events in the catalog, I plot the difference between the initiating event and the biggest events in the class. And I also plot the delta predicted by the ETAS model. We can see that the probability is more like a function of the combination given by the ETAS model, while the others have different trend. Now, when using the ETAS model to do simulation, to simulate foreshocks, there are some pitfalls. Here, I only illustrate two of them. One is the magnitude threshold issue, another is the parameter uncertainty. Here is an analysis on a synthetic catalog by using the ETAS model. Using the stochastic clustering method, I reconstruct the productivity function for the background events and for the trigger events and for all of the events as a function of the magnitude. And I also reconstruct the probability that an event is a foreshock for the background events and also for the trigger events. We can see there is no difference between those two types of events as assumed in the ETAS model. But when apply the result to the Japanese catalog, JMA catalog, we can find the difference. The reconstructed productivity shows triggered events more likely to trigger more events, and also triggered events more likely to trigger larger ones. Similar results are obtained for the New Zealand catalog and for the Southern California earthquake catalog. And is that true in the real catalog? No, it may not. In the new simulation, I simulate a huge ETAS catalog starting from magnitude 0, and then I remove all the small events, all the smaller than 3.8. Do the same procedure, reconstruct procedure to the catalog of the remaining events. And now we can see the results show exactly what happened in the real catalog. So another pitfall is the parameter uncertainty. We know that immediately after some main shock, there are more likely some aftershock missing in the observation. When ETAS model is fitted to such kind of catalog, the parameter always biasedly estimate. More likely in the parameter C become larger and parameter B becomes smaller. So the acceleration of the ETAS model seismicity before the main shock depends on those two parameters. Here, if the parameter is P is large and C is small, the acceleration is more significant. The parameter P influences this acceleration rate much larger than the parameter C. As in the Bootchain simulation, the P is quite small, about 1.02 or 1.03. Let me come to the conclusion. In my point of view, the earthquake clustering is more like a coin. The foreshock phenomena is on the head, and the Båth law is on the tail. It is hard to believe there is a focal mechanism creates the foreshock phenomena without changing any other part of this coin. Studying how the foreshock, how the tectonic environment changes, influence the earthquake clustering behavior is more meaningful than seeking foreshock only. Thank you.